In any, oh, alright, first question. In any n-bit 2's complement binary system, the 2's complement of 0 is just 0. There's no negative value of 0. No, no. It looks something like this. Something like this. Add a 1, you would get 0, 0, 0, 0, with the overflow of 1. It still ends up being 0 though. Is that right, Bertisha? A. First you'll distribute this to this. You have A bar, B bar, plus B, A bar, B bar. Well, if you look here, this is an AND gate. You have 2, you have A, and then A bar. They're inverses of each other. So if you were to have that in a little AND gate right here, then might as well be. People watch my videos now in my class. It's funny. If you had A and then A bar, like never, you need to have all the same value, right? To get that output of a 1. But since they're negations of each other, you can never have that. So, um, I forgot the theorem, but this will be 0 plus 0 because you also have B and B bar here. So the expression is B0. Okay, now this next one. We'll do AB plus, we'll distribute that C. A bar, C plus BC. So when you have something like AB plus A bar, C plus BC, see this A bar here? Well, see how they have the same uh, values assigned to it as C with both of these? Well, this lets you cancel this one. Right, and you'll just have AB plus A bar C, which is C. You can't. You can't. So fruitful. A plus BC is equivalent to. Alright, well, let's look at these expressions. Well, can't be A. You can't just swap that variable. Let's look at B. Distribute A plus AB plus BC plus AC. Well, when you have two A's like that, they can be simplified to just one A. A plus AB, right, plus AC plus BC. Well, when you have A plus AB, why are you laughing, Patricia? That's how I wasted 70% of my days last year. Now I don't have anybody. Back to the video. A plus AB. Alright. Now, what's that theorem? Need to look it back up. Nah, I'm keeping it in there. Boolean calculator. It's funny. What? Unbelievable. Alright. A plus B. A plus C. Go. Okay. The absorption law. This will go to A plus AC. You can do it again. Gives you A plus BC. So that's why it's equivalent to A plus BC. The canonical sum of product form of this function. Okay, so A plus B, what do we know? When it's 0, 0, the output's a 1. 0, 1. Or no, that's a 0. That's a 1. That's a 1. That's a 1. Okay. So for canonical sum of a product, um, we will include all the expressions in which A plus B is 1. So this is A bar B plus, actually the first one's A, yeah, it's A bar B plus A B bar plus AB, which is B. Okay, which of the following is a product of sum form? Well, product of sums is like the sum, like things being added together that do a product, which is C. Size of SRAM is 1K bits with 8 bits words. What is the number of words in this array? Well, we know 2 to the 10 is 1K bits times 8 is equal to the bytes. Well, number of words. It's tricky. Hmm, let's see. Bad Pookie, as Bertisha talks to Ben. Estrogen monster. Estrogen monster. I need a kiss to get out of bed, my Pookie Bear. That's what you sound like. With those little tapping feet. Yeah, you definitely get a kiss now. He also likes to see you get mad. Y'all are both the same person. Why are you looking at my license? You're being. What do you know about Hyper T-shirt, your hat? Ben's 5'10". You're calling him like 5'8", if that's the case. Your balls. You should do it just because you said that. Yeah, I feel like the answer is because you have the number of bits divided by the words per bit. You can find that by dividing that by 8, and that should give you 128, but that's not the answer. 7 says it's 32. I don't believe that's right. He loves making you mad. I can see right now. He's enjoying this so much. Just tickle his feet. They're particularly bad today. Tickle time.
I'm gonna kick you in the fucking face. I'll hide them. Stop. I'll hide them. I'll hide them. I'm Jamirius. If you're gonna do this to Jamirius. No. He goes with.
Wham wham. Womp womp.
Wow. Confidence. Confidence.
This is the sum of the product. There's one, two, three ones. Well, you have three variables, so that means there's 8 total output functions. Well, there's only 3 here for the sum of the product, so the other 5 must be the product of sums, which are the zeros for the outputs. So the answer is D. Now number 9, I don't know how to do it. Actually, I do. It'll compare each bit, and the output will be 0 if they're not equal.
Say it. Say it.
Is there a glitch in this K-map?
Go in there and say it.
Well, you can make there not be a glitch,
You want them out?
but if you do it the simplest way, then yes, there is a glitch. But you could easily just add one here. Uh, why would I want to?
You literally was talking about something. Bring him back. I miss him. You're a bad fucking uncle.
What's going on?
Put him on him.
Why
You have to be physically on him where he's not gonna pay attention.
are y'all going somewhere?
I'm leaving, and he's leaving.
Going to
But
go
we're not
eat.
leaving together.
Well, I'm gonna go eat then.
Hey. Consistent. Wait a moment.
This one doesn't make sense.
You know what doesn't make sense? Your face. Oh yeah. See you later.
Alright, so for 12, it's asking if 3 functions from min terms um, are to be implemented using a single decoder. What is a minimal required decoder must be? Well, you can see that we're using 15 here, so we at least need to do 2 to the 4th, which is going to be a 4 to 16 decoder, which is B. That's correct. Alright, so the 13 size of a ROM of n outputs and k address inputs is, well, the formula for the ROM is 2 to the k times n, which is B. A RAM array of 64 words, each has 8 bits, and the number of address lines are 2 to the x times 8 is equal to, well, let me think. A RAM array of 64 words, each of has 8 bits, so the total, so 64 times 8 will give you this number here. So what will that be? Calculator! 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 64 times 8. It's 512. Okay, that's the number. Alright, so if we divide that by 8, right? Divide by 8. Alright, so 512 divided by 8. Alright, we have that number. Well, if 2 to the x is equal to 64, alright, how do we solve for x? Well, we could do a little bit of natural log, natural log, x, brings down that x, divided by the natural log of 2, let's see what that gives us. Natural log of 64 divided by natural log of 2. That gives us 6. So that's how you find your answer. We can't do that in a test though. You could say what power, you could just do like what power of 2 gives you 64, and that would be 6. You could find it that way. Um, But if we had a calculator, you could do the natural log, but without it, you can't. Okay, so in a flip-flop input, data is allowed to change beyond the setup time. Well, if you look at arbiter time, right, you'll have the setup, and then you'll have the hold time right after. So technically, the input data is not allowed to change beyond the setup time because you have hold time here. So in theory, it would have to be beyond the hold time, not the setup time. So this is false. The simplest ABC, A bar C, and the K-map has this number of cells with 0. Okay. One, two, three, A, B, C. 1, 1, 1, 1, 0, 0, 1. Let's see. A bar C. So A bar. So 1, 1. So 0, 0, 0, 0, 0, 0. Well, that function would be A bar. Let's see. That is the equivalent. So there's 6 zeros. Let's check that. 16, 6. Which is A? It is A. We're right. Okay.
Into the bedroom with the suitcase on the
Alright, so we have the answers here and whatnot. So we'll have to hide it. So, considering that function, right? You're acoustic. And that's what I mean by acoustic. Okay. So for question 2, oof, we'll solve it, we'll do it on, blank. Blank here, edit. Okay. Okay. Consider the function, alright, so we have a function of A, B, C, D. Right. And we have the min terms. These are min terms, which are equal to values of 1 on a K-map. Max terms will be capital M, those are zeros. 1, 3, and all can be expressed like this can be max term. That can be used for a symbol. Any other symbol will be min term. 7, 15, these are the min terms. And then we have our don't cares, which are going to be 0, 2, 9, 10, 11, and 14. Right. Okay. So, what is the simplest product or sum of product? Well, let's pull up the old K-map. A, B, C, D. 1, 2, 3. 1, 2, 3. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Okay. So for our first one we have 1. So it'll be 0, 0, 0, 1. 1 here. Our next one's 3, which is 0, 0, 1, 1. So 0, 0, 1, 1 here. 7 is 0, 4. That's 7. So 0, 1, 1, 1. 15 is just going to be all of them, I'm pretty sure. 8 plus 4 is 12, plus 3 is 15. Yep, it's all going to be 1s. Alright, so 1 here. And our don't cares are 0, 2, 0, 0, 1, 0, x. Don't care 0, 0, 1, 0, 1, 0, 1, 0, 1. 10, which is 1, 0, 1, 0. Oh, that's 10. 9 is 1, 0, 0, 1. So, wait, my bad. That's wrong too. 0, 1, 0, 1 is 5. That's not a don't care. My bad. 9 is 1, 0, 0, 1. So 1, 0, 0, 1. And 10 is 1, 0, 1, 0. 1, 0, 1, 0. 11 is 1, 0, 1, 1. 1, 0, 1, 1. Don't care. And then 14 is 1, 1, 1, 0. Right? Yep. So 1, 1, 1, 0. Okay. These are the rest of zeros. So what is the sum of the product? Well, the simplest sum of a product, we have to do the biggest circling, which is here and here. And that'll come out to be A, B, bar, bar. That's it. Plus C and D. Now let's compare that to the answer. That is correct. Now let's do the product of sums for this. The product of sums would be looking at the zeros. So, let's see what we can do with that. So there's this 0 down here. We could do, let's try this. 1, 2, 3. So we got 1, 1, 2, 3. Alright, that comes out to be for this is the sum of the product. Product of sums is equal to B D bar plus C bar D bar plus C bar B. Let's see if that's right. Oh, product of sums is done differently, I forgot. It's instead of doing it like that, you'll do B plus D bar. Alright, and you'll do C bar plus D bar. And you'll do C bar plus B. That's not bar. Okay, C plus. So he has 1, 2, 3 circled. So there's many ways to do this problem, but he has 3 circled to do all of them. 1, 2, 3, which sounds about right. C plus A bar. You can get many different ones, but when you do the circuitry, it'll be the same. But you should only have 3 circled. boss has messaged me. Please send me your school schedule for next semester and let me know any other time you would be unable to work. Okay. Alright. So for the simplest sum of a product, is there any glitch? Well, no, because the circlings are interlapped, as you can see here. There is no glitch. Well, how does he check it? Well, that's what it means. Is there another way? There might be another way to explain it, but the same goes for the product of the sums. There is no glitch. And D asks, implement the simplest sum of the product part A into a 4x1 mux. Well, that's pretty simple. Sum of the product is A bar. Oh, to implement a mux, we would have to create a truth table. So, let's see. So we have A, B, C, D. Then we'll have F, right? So we'll have all the combinations. 1, 0, 0. This will be 2. 0, 0, 3. 0, 4. 5. 6. 7. 8. 9. Ah, damn, this is long. 8, 9, 0, 10, 11, 12, 13, 14, and 15. Alright. So we know originally that we know the midterms, right? 1, 3, 7, and 15. So when it's 15, there's a 1. So 1, 3, 7. So 1, 2, 3, 4, 5, 6, and 7. The rest are zeros. Well, realistically, most of these are don't cares. Let's see how. Let's make sure. So 0, 0, 0. All right. Okay, so what I see being noticed is when I made that sum of a product, those don't cares can either be a 0 or a 1, right? But when I circle them in the function table, they do become a 1, right? So I did circle these, right? 0, 0, 0, 1, which is 1. But no, 0, 0, 0, 0, 0, which is 0, is circled, so that has to become a 1 now, since it is a don't care. It can 0, 0, 1, 0, which is 2. That was circled, so it has to be a 1 now. Alright, let's look at we have one more, which is 1, 0, 1, 0, 1, 1, which is 8, 11. 1, 0, 1, 1. So let's make that. What is it? Create a 4-to-1 mux. Okay. So we'll have A and B coming in. You'll get 0, 0, 0, 1, 1, 1, 1, 0, right? Then we'll have C and D. Okay. So when C and D, so 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. So when, as you can see here, right, no matter what, it's a 1, right? Despite it being when this is 0, 0. So that's going to be power. Then you have this function here. When it is 0, 1, well, the only time it becomes 1 is when C and D are 1, 1. So it looks like that's an AND gate. So, C and D. And we have another function here. Another AND gate, which is for 1, 0. And then we have 1, 1. Another AND gate. Here. Yeah, they're all, yeah, it does match up. These all go to the AND gate. Okay. And that's the mux. That is the mux. Okay. Next question. That is the 4x1 mux. Or is it 4? I think it's 1x4. Is it 4x1? It is 4-to-1. 4-to-1 mux. Okay. So next question. That's 5 parts. Part A, B, and D are 5 points each. Part C is 6 points. Part E is 7 points. Okay. Then we're going back to here. And there's the answer. Okay. Question 3. 28 points. 5 parts. A, B, and D are 5 points each. Part C is 6. Part E is okay. The 4-to-1 multiplication below is used to Boolean function represented by a truth table. Label the missing information on the circuit. So, well, like usual, you'll have these two first functions represent the selects up here, right? And then you'll have W3 probably being a function of the outputs down here. And let's see. Let's look here. Despite right here, despite W3 changing, which is going to be our select, it's still 0. So that's going to be ground, right? And we have here, it does 0, 1 is a function of W3. So it's going to be connected to W3. And here, it's also a function. So 1, 0 is going to be another. And then we have this one. Despite the changing of W3, it's going to be connected to the power, which is 1. Well, make sure to use your symbols, right? You can't just put 0 and a 1. That's that one. Pretty simple one. Implement the following Boolean functions on a single 3 to 8 decoder, and using only a single output gate for each function. You may select the single gate the way you choose. So the first function, F1, AB plus A bar C bar. So implement the following on a single and using only a single output gate for each function. A single output gate for each function. Okay. Alright, so for the first one you have A, B. plus A, B bar, C bar. Right. So how would you implement this? Well, you'll see that A, B is only two variables. Well, and then you'll see how it changes to 3 here. Well, how do we do that? Well, I remembered trick. Right. So we have 3 selects. So let's do this. We'll do this. We'll make a truth table. A, B, C. Go back a little bit. This makes it easy. So say we have AB plus ABC. So 0, 0, 0, 1, 1, 1, 1, 0. Here's a good way to do it. The Boolean expression way to do it's a little bit hard. This will be easier. So AB, AB. So we'll have 1, 1. That represents AB when you circle these, and then we need A, B bar, C bar. So that'll be A. How do we get that? A, A, B bar, C bar. That'll be a 1 here, circled by itself, right? That is how it's implemented. That is how it's circled on the table. This single. Well, we can change that, right? Oh, sure, that's too much. We can change this. We can circle it different, right? We can do it like, well, if we're using a decoder, how we can change this is we can circle each of these by themselves, right? And that'll give us a different expression. So we'll have A, B, C plus, the next one's A, B, A bar, B bar, and no, these aren't bar. They're positive. C bar plus A, B bar, C bar, right? And that gets you this function right here. Exactly what we needed. Exactly.
I'm skipping this class. You already put our attendance rate.
Good boy.
Schoolwork.
So this is the easy way to get that expression, right? Because for the decoder, you have you have 3 selects, and you can't just do it with AB. AB, you'll have to use more than one. You have to change the expression because there's not just AB here. It's all 3, A, B, and C. So what you do is you make the K-map of the expression, and then you change it to circling each individual one. So then you'll get 3 variables for each uh, min term, and that'll let you select what you want. So the first one is 111, 110, right? And then 100, and they all go into an OR gate. They all go into an OR gate. And then for the next function, we will try to do the same thing. So we have A plus B bar plus C. Well, to represent that on this table, alright, let me try to erase this. How do we do that? So, to get the expression A plus B bar plus C, you're circling some big loops. Some big ones. So for A bar, for just to get A by itself, you would have to do 1, 1, 1, 1. And for the next one, for B bar, you would have to do 1, 1, 1, 1.
You sure it's only one?
It would be this one. Alright, and then for C by itself, you would need a 1 here. There's 1, 0 here. So how do you go from here? Well, we have that 1 0 in the way. But that is the expression. And we need groups of 3. Well, the way to do this one might have to be the algebraic way to do it. You might have to do that algebraically. Let me think. Yeah, just doing it, writing it, circling each little one might not be the way. Because if you were to do it this way, you would have 0 0 0, right? This one. And you would have every single other one but 0 1 0 going in. But if you put an inverter, it's the opposite. Interesting. Interesting. Because if you take that inverter away, the expression would be all of these, right? All of these going into an OR gate, which would technically be the same answer. You can do it that way too. That would get you the right answer. But what if you did the product of sums? Well, that would be A bar B. No. The expression would be A plus B bar plus C. That's the product of sum expression.
No way.
That is what is up there. So the other way you could do this is by doing everyone but 0, 1, 0, 2, and OR gate. That would give you the same answer. It's probably easier to do it that way instead of the Boolean algebra. But he uses De Morgan's theorem here. And when you have that double bar, you can bring them all together. Well, when they're all underneath the bar, right? You can multiply them together, and the bar negates that B bar, so it's just A bar B plus C bar, or times C bar. But you still have another line up top. But you can like factor it out of the radical and have it out here. Make it prime. So you'll have that function, right? A bar going in, which that is equal to an inverter. You could also think it as of if you were to do this whole expression, right? The inverse of it would be the product of sum, which is 0 and 0 with an inverter. Which is interesting to notice. There's more than one answer to this question. It's weird. Anyways, next one. Consider the AU shown below. What is the value of the output y if the function SLT is performed? Set less than. Well, 1, 1, 1. You pick 1 here. You grab the 2's complement. Alright, so you'll have 1011 minus 0011, which is, you'll add these together. You'll get 1, I'll start the red. 0, 1, 1, 1, 1, 1, 1, 1, 1, which is equal to negative 8, 4, 2, which is equal to 2. Negative 2. Alright? Because we have the first number being 1, 11, minus 8, 12, 13, which is negative 2. Yeah, that's the answer. So since it is negative, the output, the output is a 1, right? And C out is 0. There's nothing being carried out here. C out is the last carry out. So if it was 1 plus 1, then there would be a C out of 1. But there is no C out, so we're good. Shifter. We haven't really gone over shifters. So the counter shown below. If the counter is initialized to Q 0000. Okay. It's initially 000, right? So somewhere along the way it gets inverted. D is inverted. D, the second one gets inverted. So it gets passed through, but D gets passed back around inverted. So see, the D gets inverted, right? It gets put to the front, so we'll have 1, 0, 0. The value of D gets inverted again, so we'll get 1, 1, 0. D gets inverted, but D's a 1, so we'll get 0, 1, 1. The 1's move up. It's a 1 again, so you get 0, 0, 1. Oh, there's a 1 again, or 0, so it goes to 1, 1, 0, 0. Then 1, 1, 0. See that cycle? So does it match? Yep, that's how it's done. Counter is said to be mod 4. You just have to remember that one. Alright, given the state diagram of the sequential circuit above, input X and Z, identify the circuit type. Is it Mealy or Moore? Well, the inputs and the outputs are a function of each other. So that's Mealy. But if you have the outputs a function of the state, then it's a Moore. Derive the state table based on the circuit above. That one's pretty easy. Oh, we'll do it on Scratch. Let's see. Let's look at how many questions we have. Some more K-maps. This is a adder. And that's it. There's not much more left. We'll do this one. Not a bad study session, to be honest.
Really?
Making good progress.
It's good, man. I'm glad for you. Happy for you. Dude, my final exam for my comm class is open textbook.
Huh?
My comm class is open textbook. The final exam.
taking advantage of that.
Yes, sir.
Maybe this music does help. Maybe I'm a believer. Ben, you'll dog on me for what I'm listening to. You ready? Study music alpha waves. Relaxing study music brain power.
That's retarded.
Having a good study sesh says otherwise. These powerful brain waves. Powerful. I'll take anything I can, even if it's, what is that effect? Like you think it works, but it don't do actually anything.
Huh?
It doesn't do actually anything, but you just think it does.
Placebo.
Placebo. I'll take placebo if it works, even though it probably doesn't. All right, I need this. Pull it up. All right, we'll make a circuit based off this diagram. Okay. I have it pulled up on another tab for information. All right, so we have what is this? So we have four functions, four states, 0, 0, 0, 0. So it goes from 0 to 2 to 3. So
Get your
0,
ass.
0,
This fucking idiot.
0, 1, 1, 0, 1, 1. Alright. And each can have two different inputs for one. So let's start off like this. Alright, we'll have X here. The inputs, our states will be here, present states. Function function X will be inputs. So we have 0, 0, 0, 0, 1, 1, 1, 1. Because each state can have two inputs. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. And we have our next states. Then we have our outputs. Alright, let's look at the table. So if the inputs is 0 and the present state 0, 0, what happens? Well, the next state is 1, 0. The output is a 0. Input 0 for 0, 1. Oh, I was wrong. Yeah, no, that's right. For 0, 1. If 0, 1 gets a 0, well, it goes to itself. And the output's 0. For 1, 0,
Hey, babe.
if you get a 0, it goes to 1, 1.
You said what?
And output's a 0. If 1, 1 gets a 0,
It's going alright.
it goes to 0, 0.
I'm trying to figure.
Output's a
He
0.
doesn't have the rubric for it, so
Well,
I
0,
don't
0
know
gets
if
a
it's
1,
right.
goes to itself,
But
and the output's 0. If 0, 1 gets a 1, it goes to itself,
gotta
but
check
the
it.
output's a 1.
Let me
If
try
1,
it.
0 gets a 1, it goes to 1, 1,
Oh, fall
and the
pollen.
output
I found it.
is a 0. If 1, 1 gets a 1, well,
You I don't
it
see
goes
it.
to 0, 0, and the output's a 1. So there's two functions with output 1, so it detects 0, 0, 1, and it
Name
detects
yourself.
just the number 1 in the second
Behind
state.
me.
You would have to start
You
at 0,
fucking
1.
over?
A little weird. Okay, next part is um, derivative state table. A is a T flip-flop, and B is a JK flip-flop. So A is the first variable.
What?
So A, T, A. Let's pull up a state table.
That smell like syrup? Yeah, it sucks. Yeah.
Need to pull up my state table real quick.
Gotta take into account. Alright, I'll see when you get here. I love you. Because I want to play.
Okay. So, still trying to pull up the table. Let's look at it here. D flip-flop specification. Okay, so if it goes from 0 to 1, it's a 1. 0, 0 is a 0. 1, 1 is a 0. 1, 0 is a 1.
Fuck.
0, 0 is a 0. 0, 0 is 0. 1, 1, 0. 1, 0. 1. So if it's the same, it's a 0. If it's different, okay. 0, 1, 1, 0, 1, 1, 1. Boop, 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 boop. Okay, we're good. Checked it all. So next one, we making a JK flip-flop? Yep. So JK has two functions, J and K. For B, okay, so 0, 0, 0x, 1, 1, x 0, 0, 1, 1x, 1, 0, x 1, 0, 0, 0x, 1, 1, x 0, 0, 1, 1x, 1, 0, x 1. That's a JK flip-flop. Alright. So let's see if it matches 0x, x0, 1x, x1, 0x, x0, 1x, x1. Yeah, we're good. That's the state table. Okay. And that concludes that question. We can go back here now. Alright, so if the initial state is 0, 0, and the input is 0, 1, 1, 1, 0, 0, 1, where 0 enters the circuit first, what are we dealing with here? So we want the output and the last state. So let's look at the state diagram. So if we have, we're starting with 0, right? So 0, next state is 1, 0. We'll make the next states here. So we go 1, 0, and Z will be the outputs. 1, 0, output is a 0. Input 1, 0 is a 1. You go to 1, 1, output's a 0. Next one's a 1. You go to 0, 0, output's a 1. Next one's a 0. You go to 1, 0, output's a 0. Get another 0. You go to 1, 1, output's a 0. Um, so 0, 1, 1, 0, 0, 1, 0, 1, 1. And the next one's a 1. We're at 1, 1. We get 0, 0. Output's a 1. Which is here. So we're good. Oh, we need to design the circuit now. Alright, let's go back to here. So we need to make one for TA. JB. KB. And Z.
Fuck. No.
Okay. So TA, we have A, B, and X. Right. So we have the present state. Okay. Okay, so when AB is 0, 0, right? The input's a 0. The output's a 1. When you have 0, 1, right? You get 0. 1, 0, we get a 0. 1, 1 is a 1. Then we got 0, 0, 0, 1. Alright. So our function's going to be this. There's a little bit of a glitch there, but that's fine.
Getting it. Level 9. Damn it! I'm done. Wait till the 10.
Okay. So for the JB, we have 0, X, 1, X, 0, X, 1, X. Boom. I'm gonna write the algebra functions. Or Boolean functions, I mean. This one will be just A. This one will be AB plus AB bar X bar. And then for this one, 1, 1, 1, 1, 0. We have 0, x0, x1, x0, x1, x0, x1 again. Here's your function. We got another A. Then Z is 2, 3, A, B, X, function is 0, 0, 0, 0. All these are just gonna be all 0. And we got 0, 1, 0, 1, 0, 1, 0, 1. B, X. Okay, cool. Let's compare. A, B, C bar plus AB, right? A. Doesn't do one for the output. What kind of circuit is it? It's a melee? Yeah, it's not a sequential circuit. Yeah, there should be some Z value. There is no Z. There's always one for the output value. We always do a function for the output. Um, Weird. Yeah, but the output is a function of the input, so that's how you know it's a melee. Anyways, last question. We'll go to here. Where is the file? Last question. Here. So, circuit 4-bit adders using compute the term y minus 2x, where x is 0, 0, x 1, x 0, or y is
That's cool.
hmm,
Why is the phone in your face? Why is the phone in your face like this? Adaptation. Why?
okay. Shit.
You're big?
Shoot. I mean shoot. Where's my phone? I dropped it. My neck hurts.
You need a cane? Yes.
Okay.
Lethal Company? Oh, you're doing? Oh.
Hmm. It makes sense, but why does x1? Okay, so it makes sense because these we'll call this the value is binary, right? It'll fill in here from left to right, right? But for x, it doesn't do that. It's 0, x1, x. It moves up for some reason. Well, x is multiplied by 2. It has to do something with that, right? So what if you have the expression 0, x1, x 0 times 2 times 2? Well, if you'd add itself, that's the same thing as multiplying anything by 2. It's so anything x0 plus x0. Hmm, interesting. Interesting. Well, when you perform subtraction, the 1 comes in here. That makes sense. So why does this expression move over? Need to figure that out. Well, let's say you have 0. Well, we won't put that there. We'll just make them x, right? Well, when you multiply by 2, it's basically it's adding itself, so something plus it's equal to 2x, right? Well, you can't have 2 in binary, so we'll make that a remainder of 0. X plus x plus x, you'll have x left over, but you carry over an x, right? But you're left with x and 0. So it makes a little bit of sense. We can say that when you're adding variables, well, they're equivalent to 1, right? But you have to remember that these will correspond to what variables they were, which is a little interesting. So I would say that's how you do it, right? You pretend they're like a 1 and how you're adding it, but you gotta remember their placement in the operation. Because multiplying anything by 2 is the same as adding itself. Like 1 times 2 is 2, which is equal to 1 plus 1. 3 times 2 is equal to 3 plus 3, which is 6. It's all the same thing. That's all. That's the last question. So, yep, that's that. That will be